Welcome back, Apologia, Physical Science, Week 20, Day 3. This is actually the first 7 questions of the study guide for Module 9. All right, match the following terms to their definitions. All right, mechanical wave. It is a disturbance in matter that transfers energy through the matter. Mechanical waves start when a source of energy disturbs matter in some way and causes a vibration to travel through the matter. All right, the second is a transverse wave. What is the definition? A transverse wave is a wave in which the medium vibrates at right angles to the direction the wave travels. It is a type of a mechanical wave. All right, longitudinal wave, think slinky toy, think sound wave. A wave in which the vibration of the medium is parallel to the direction the wave travels. It is a type of mechanical wave. A surface wave is a wave that travels along the surface of a medium. It's a type of mechanical wave, think ocean. Ocean waves are surface waves. Supersonic speed. Any speed that is faster than the speed of sound in the medium of interest. All right, so think of this for an example. If a jet airplane travels in air faster than the speed of sound in that medium, air, we say that the object is traveling at supersonic speeds. And the speed unit for that is known as its Mach number. Pitch. Pitch is an indication of how high or low a sound is, which is primarily determined by the frequency of the sound wave. Now, please remember that the terms high and low do not refer to volume. They refer to like the musical scale. Doppler effect. A change in sound frequency caused by the motion of the sound source, the motion of the listener, or both. All right, number 2. In designing a car's horn, the engineers test the sound of the horn and decide that its pitch is too low. To adjust the horn, should the engineers change the electronics so as to produce sound waves with longer or shorter wavelengths? All right. The engineers would need to adjust the electronics to emit sound waves with a shorter wavelength. Remember, wavelengths and frequency are inversely proportional. If the engineers want a higher pitch, they want a higher frequency, which means they have a shorter wavelength. So again, just try to remember sound waves with long wavelengths have low frequencies and low pitch. Sound waves with short wavelengths have high frequencies and high pitch. A sound wave is traveling through air with a temperature of 30 degrees Celsius. What is the speed? All right, so step 1, always write down the list of knowns and unknowns. We know the temperature, we know the speed, or we are trying to solve for the speed. Step 2, write out the equation. We did. Step 3 and 4, substitute numbers into the equation and solve. So there we go, 349.5 meters per second is the speed of that sound wave. Question number 4. If the sound wave in problem 3 has a wavelength of 0.5 meters, what is the frequency? Step 1, write down the list of knowns and unknowns. We have the wavelength of 0.5 meters. We have the speed of 349.5 meters per second, and we're trying to find its frequency. Step 2, write out the equation. All right, so we have the speed equals the wavelength times the frequency. But really, we want to solve for the frequency, so we have to divide both sides by the wavelength to figure out that the frequency is the speed over the wavelength. So step 3 and 4, substitute the numbers into the equation and solve. So we get 699 1/2 or 699 hertz. Question number 5. A sound wave has a speed of 345 meters per second and a wave of 500 meters. Is this wave infrasonic, sonic, or ultrasonic? We should probably first start with what the definition of infrasonic is. Infrasonic waves have frequencies less than 20 hertz. Ultrasonic waves have frequencies greater than 20,000 hertz. And sonic waves have frequencies between the two, between 20 and 20,000. So now, step 1, write down the list of knowns and unknowns. We know the wavelength is 500 meters. We know the speed is 345 meters per second. We need to solve for the frequency. Step 2, write out the equation. Step 3 and 4, substitute numbers into the equation and solve. So the answer is 0.69 hertz. All right, so since the frequency is less than 20 hertz, it is an infrasonic wave. Question number 6, a physicist takes an alarm clock and put it in an airtight chamber. When the chamber is sealed but still full of air, the physicist is able to hear the alarm despite the fact that he is outside of the chamber. If the physicist then uses a vacuum pump to evacuate essentially all of the air out of the chamber, will the physicist still be able to hear the alarm? Why or why not? All right, the physicist will not be able to hear the alarm because without air, the sound waves from the alarm have nothing through which to travel. Thus, they cannot make waves, and as a result, there just is no sound. And last, for this video, what kind of waves are sound waves? Sound waves are longitudinal waves.